In this video, we're going to be looking at trig equations that have compositions in them. So by composition, what we mean is something like this, where inside the argument of the trig function, we have something getting multiplied. So this right here, 3 times x, that's the composition that we're talking about. Okay, so how we solve something like this is we first don't even need to think about the 3 times the x. We want to ask ourselves what value, or rather, what angle, I should say, because 3x represents an angle. What angle has a cosine value of 1/2? Okay, and this interval here, 0 to 2 pi, is telling us we want to know what angle in radians. Okay, so thinking about the unit circle, cosine is positive in quadrants 1 and 4, and it's equal to 1/2 at these locations. So in radians, that's going to be pi over 3 and 5 pi over 3. So what we do, I'm going to rewrite the equation down here. Cosine of 3x is equal to 1/2. And when we answer this question, the two angles are pi over 3 and 5 pi over 3. So what we do, we branch this off into 2 branches because there are 2 angles. We say 3x is equal to pi over 3. And then we say 3x is equal to 5 pi over 3. And what we need to do when we have a multiple of an angle like this, 3 times x, we actually add 2k pi to each of these. And then what we need to do is we need to test values of k to make sure that we're between 0 and 2 pi. So let's go ahead and do that. And we'll go through this, and then we'll talk about why we need to add that 2k pi to each term, or to each equation. All right, so to solve for x, I'm going to divide both sides by 3. Pi over 3 divided by 3 gives us pi over 9. 2k pi divided by 3 is 2/3 k pi. And then on the right equation, we're going to get 5 pi over 9 plus 2/3 k pi. Okay, so what we're looking for are angles in this interval. So what we're going to do is we're going to test values of k. So if k is equal to 0, we get x is equal to pi over 9 plus 2/3 0 times pi. This term goes to 0, we get pi over 9. Is pi over 9 in the interval? Yes, pi over 9 is between 0 and 2 pi, so that's good. And we proceed in this fashion until we reach a value that is not in that interval. So if k is equal to 1, we're going to get pi over 9 plus 2/3 1 times pi. 2/3 times 1 is just 2/3. I'm going to write that with a common denominator, so 6 over 9 pi. Okay, so we get pi over 9 plus 6 pi over 9, which is 7 pi over 9, and that is also in the interval. Let's check k equal to 2. I get x is equal to pi over 9 plus 2/3 2 times pi. We get pi over 9. 2 times 2/3 is 4/3. Getting a common denominator, I'm going to get 12/9 pi. That gives us 13 pi over 9. And again, that's greater than 0, but it's still less than 2. And then let's check k is equal to 3. I get x is equal to pi over 9 plus 2/3 times 3 pi. 2/3 times 3 is going to be 6 over 3, which is just plus 2 pi. Now, pi over 9 plus 2 pi over 9, well, that's 19 pi over 9. 19 over 9 is bigger than 2, so this is not in the solution. Okay, so on this left branch of the equation, we end up with pi over 9, 7 pi over 9, and 13 pi over 9 as possible solutions. And then we need to go through this exact same process for the right branch of the equation over here. So why don't you hit pause, try this on your own, and see if you get the same equations, or the same values that I got. All right, so here are the three values that are going to work. And then 24 pi over 9 is not a solution. So I can add these values to the list of solutions. And so there are 6 angles that will make the original equation true. And now let's look at the graph of the original equation and see what we have and how the solutions, how we can visualize the solutions. Okay, so our original equation was cosine of 3x is equal to 1/2. So when we're trying to solve an equation, we can do this graphically by splitting up the left side and the right side of the equation as 2 separate equations. So y equals the left side, y equals the right side. So y is equal to cosine of 3x, that's the cosine curve that we see there. And then y is equal to 1/2, that is this line right here. So all of the intersection points are what the dots are on the graph. And so we have an intersection point at pi over 9, 5 pi over 9, 7 pi over 9, 11 pi over 9, 13 pi over 9, 17 pi over 9. And then this green vertical line is x is equal to 2 pi. That's the boundary. We wanted everything between 0 and 2 pi. Where do these two equations, where do the graphs intersect? Now, we have 6 intersecting points here. If we were, and think back to how we graph something like this, cosine of 3x. Well, cosine of 3x, that 3 is a horizontal compression, so it's taking the curve cosine of x, which would look like this, and what it's doing is during that same length, it's compressing it, so it's kind of like taking a spring and pressing it together. So by doing that compression, that's why we end up with so many more intersecting points, and therefore so many more solutions to the original equation. All right, let's look at another one. We have a composition again, x over 2 inside the sine function, and our interval is 0 to 2 pi, so we're in radians again. So the question we want to ask is, when does sine equal negative root 3 over 2? Well, sine is negative in quadrants 3 and 4, so it's in these locations. Those angles in radians are 4 pi over 3, 5 pi over 3. So we're going to split this into 2 branches. We're going to say 4 pi over 3. Let me write that the other way. We're going to say x over 2 is equal to 4 pi over 3 plus 2k pi. And then we're going to say x over 2 is equal to 5 pi over 3 plus 2k pi. So just like we did previously, we're going to test different values of k and then solve for x. So if k is equal to 0, we're going to get x over 2 is equal to 4 pi over 3 plus 2 times 0 pi, so that is equal to 0. So we get x over 2 is equal to 4 pi over 3. Multiply both sides by 2, we get 8 pi over 3. Well, 8 pi over 3 is outside of this interval. 8 over 3 is bigger than 2, so there is no value there. And if we get values that are bigger than k equals to 0, so k is equal to 1, k equal to 2, etc., etc., we're going to get bigger and bigger angles here. So there seems to be no solution for this left branch. If we test k equals 0 on the right branch, we're going to end up with the exact same problem. So we get x is equal to 10 pi over 3, which again is bigger than 2. So what we'd say here is that there is no solution. And actually, let's look at the graph of this one too to see a visual of this. Okay, so once again, the red curve is y is equal to sine of x over 2. And then the blue line here is y is equal to negative square root 3 over 2. And then 2 pi is here and 0. So what we see is in that interval, the sine curve does not hit y equals negative square root 3 over 2. And so when we think about this equation, sine of x over 2, what that is that's taking the sine curve and it's stretching it out horizontally. If we were to graph this right here, well, that's going to be, let's see if I can do this smoothly. I'm going to end up with, hang on, it's going to cross at about pi, so the curve is going to do something, go down like that. So that would be y is equal to sine of x. And what we see is we have two intersecting points there, but once we stretch out that curve to be this red curve, that curve is no longer going to be hitting the line y is equal to negative root 3 over 2. So this is why we get no solution. Okay, so tangent of 2 theta is equal to square root of 3, and we want this between 0 and 360 degrees. So just to reiterate, this means we want the solution in degrees. Okay, so we want to ask ourselves, when does tangent equal square root of 3? So tangent is positive, quadrant 1 and quadrant 3. So it's at these two locations. That's pi over 3, 4 pi over 3. So what we're going to do is we're going to say 2 theta is equal to pi over 3. Oops, we want to be in degrees. So we want these measured in degrees. So 60 degrees, and then this angle down here is 240 degrees. So instead of writing pi over 3, we're going to write 60 degrees, and then I'm going to add 360 degrees times k. Okay, so divide both sides by 2. We get theta is equal to 30 degrees plus 180 degrees times k, and then we'll test values for k. In the second branch of the equation, we're going to get 2 theta is equal to 240 degrees plus 360 degrees times k. We end up with theta is equal to 120 plus 180 degrees k. So again, we're just going to test values for k to find angles that are between 0 and 360 degrees. So why don't you hit pause and see if you can find these values. Okay, so we end up with these 4 values that are going to work, that are inside the interval 0 to 360 degrees. So our solution is just a listing of all of these. I'm going to write these in order. And there we have it. Okay. Now one thing that we can do for anytime we have a tangent equation, so what we notice is that anytime we look at the solutions for a tangent equation, they're always going to be 180 degrees apart from each other, or pi if we're in radians. So they're always on complete opposite sides of the circle. So what we could do is, instead of branching off into 2 branches here, we can start this by just branching using a single branch. Okay, so if I said 2 theta is equal to 60 degrees plus 180 degrees k, because the solutions are always 180 degrees apart from each other. Now this is different than sine and cosine, where they're not always exactly opposite in the circle. So if I solve this, okay, I end up with a general equation of theta is equal to 30 plus 90k. And now if I make k equal to 0, I get 30 degrees. If k is equal to 1, I get 120 degrees, and so on. And k is equal to 3, that's 300 degrees. If k is equal to 4, that's 390. And that's where I go too big. Okay, so we could do one branch anytime we have a tangent equation. We could still do two branches and always do them the same as when we have sine and cosine by adding 360 or 2 pi.